Okay, so let's continue. So so given this matrix, we are talking about the determinant of a matrix, and this determinant of A, if it is 0, and then it means the matrix is a singular or non-invertible, and if it is not 0, and then it is non-singular or invertible, right? And also again, the determinant is defined only for the square matrix, so we don't. It doesn't make sense to discuss the determinant for rectangular matrix. And then in this matrix, given the matrix, how we compute, the way to compute the determinant, in this particular example is to utilize something called the cofactor formula. And so here it is like this. So our strategy is to pick up the columns or rows that has the most non-zero values. So this is this guy, or maybe this guy, is the column or row that has only one non-zero. So let's start with this guy. And then we typically do this guy like this kind of pattern, right? And so this plus and this minus, and so it is minus. And then given this minus sign and also 1 here, and this -1 times the determinant of the submatrix after discarding or removing the corresponding rows or row and column, right? And then and then that small matrix, that small matrix determinant is multiplied by -1, and then we can now reduce the matrix size to compute the determinant of. And then given that, we also have we also pick up now this row, right? And then it will have the pattern of plus and minus, because we removed this guy, and minus and plus, and so it is like 3 times 3 times the determinant of the matrix that has the smaller size, right? So in that case, we remove these two these rows and this row and column as well, right? Then given the remaining element of 3 by 3 matrix, 3 by 3 matrix, and then for example, like this kind of 3 by 3 matrix, for the 3 by 3 matrix, there is one kind of convenient formula that can be used for computing the determinant. And how we compute the determinant of 3 by 3 is as follows. So we compute the product of these 3 numbers, and these numbers and these numbers, right? So again, 4 times 0 then 0, and we compute that product, and 0 times -25 and 0, which is we compute the product of these 3 numbers, and we compute this guy 3 times 25 and -2. We just multiply these 3 numbers, and then we add these three numbers together. Okay, so for each product, we multiply 3 numbers, and this and this, and then only one product of 3 times 25 and -2 will produce non-zero, right? And then and then we subtract from that number the other 3 products of this guy and this guy and this guy, right? So in this case, yeah, 3 and that one also involves 3, and this guy times this guy and this guy is the only non-zero term. Thus, we just subtract that from the previous one, right? So that's how we compute the determinant of this 3 by 3 matrix. Okay, so back to this problem. Although there are four matrix, I mean that has non-zero elements in the remaining 3 by 3 matrix, but yeah, we if we apply that formula, and although I mean yeah, it seems to be computationally a little bit challenging, but I think yeah, you get the idea of how to compute this determinant. And regarding this determinant, I mean computing the exact determinant value given a matrix, I mean in these days our programming languages such as Python or R or MATLAB will just compute automatically the determinant of a given matrix. So it doesn't, it is not much important to actually compute the determinant of a given matrix by our hand, right? But it is important to know that know the meaning of the physical meaning of the determinant. So this determinant is having, I mean the meaning, I mean the physical or intuitive meaning of the determinant is, for example, suppose our matrix A has the determinant of 5, and then it is, yes, let's see, suppose it is 30, and then it actually means the ratio of the volume of the output from the unit ball or unit kind of square. So what it means is as follows. So if you think of this A times X, and then suppose A is 3 by 3 matrix, okay, 3 by 3 matrix, and then 1 0 0 and 0 1 0 and 0 0 1, for example, and then we can think of the volume of the unit unit cube, for example. So this is an X, Y, and Z, and so okay, so so this guy is a 1 0 0, and this guy is 0 1 0, and this guy is 0 0 1, right? So in this case, what is the volume of this unit cube? It will be 1, oops, right? And then let's imagine the resulting it is not a parallelogram, but it's a little bit volumetric kind of parallelogram, right? So this 1 0 0 is mapped into some vector, and this is a 0 1 0's output, and this is a 0 0 1's output. Okay, and then suppose we are given these 3 vectors that has the different directions and also different different angles and also different lengths in terms of this vector. Okay, so suppose this one is output of 1 0 0 0 and 1, 0, 1, and 0, and 0, 0, 1. And then we can imagine some like volumetric version of the parallelogram, right? Right? You can imagine that. And then we can think of the volume of this volumetric kind of parallelogram, right? And then what is the actual volume of that kind of, yeah, three-dimensional parallelogram? So that volume is 30, right? So if our volume was 1, and then we just multiply. So this is this ratio of this volume increase that is indicated by our determinant. Okay. I mean, we don't give a we don't do any rigorous proof, but you can intuitively have a sense or understanding of this determinant. I mean, its physical meaning. And what if it is having 0? And then why is it having 0 volume in this case? So determinant being 0 means that they are linearly dependent columns, right? So starting from 1, 0, 0 and 0, 1, 0 and 0, 0, 1, and it has a three-dimensional volume, right? But if we map these three linearly independent input vectors, and then if we consider their independent, I mean respective mapping through A times X, and then if A has linearly dependent columns, or in other words, if it is a singular, and then given these three resulting vectors, they will be, I mean their span will be only two-dimensional plane, right? So in this case, if we consider their volume, and then volume is really becoming kind of flat parallelogram, right? And so if we consider it's a volume, and then the volume becomes 0, right? So that way, we can also think of this determinant as this ratio of the resulting volume compared to their input volume. And also this determinant has also interest, in terms of this volume stuff, we can also think of this determinant in terms of our eigenvalue and eigenvector. And so in terms of an eigenvalues, how do we represent this determinant? What's the relationship between eigenvalues of a matrix A and its determinant? So let's first check the formula. Okay, so Google is already giving the answer. Determinant and the eigenvalues and product. So in other words, let's see. Although it doesn't show the nice formula, but determinant of A is equal to the product of its eigenvalues. Okay, so this determinant of an A is just product of our eigenvalue. Okay, so we have some mechanical way of proving that. I mean, it is not that difficult, but I mean, I just wanted to talk about or discuss the intuitive meaning in terms of its volume. Okay, so if we start from this, the unit cube, but also we can think of this unit cube as, rather than this unit cube, we can think of the unit sphere that has the center at the 0 or origin. So what it means is It is a little bit difficult to draw, but yeah, we can think of some ball or sphere in this three-dimensional space where the radius is 1 for every direction, and yeah, of course it's a sphere, and also yeah, they are centered at the origin, right? And then see. So when studied this induced matrix norm, right? So you guys imagine this kind of figure. So so if we have a rectangle in the input space of maybe 1 0 and 0 1, and then 1 0 may be becoming this vector after multiplying with the matrix A. So A times X is this guy, and the second one, 0 and 1, is transformed into this vector, right? And then if we think of this unit rectangle, I mean the square in the two-dimensional space will be transforming into that parallelogram, right? So in this case, I mean, if we apply this determinant, and then if 2, 6, 5, 3, and then what is the determinant? It is 6 minus 30, and thus negative 24. And I forgot to mention one thing. So in terms of a volume ratio, the determinant, I mean, we need to use an absolute value of the determinant. Okay, so that actually, I mean, if that is reversed or that has the negative sign, and then it means some vector has this kind of negative direction. I mean, although it is whether it is really the negative direction or not, but yeah, I mean, it is not clear. But yeah, we can think of like a volume that has the negative edge. I mean, negative length edge, right? But anyways, so if it was 1 and 1, and if we change it, the length as 3 and maybe 5, and then what is the so it is not clear. I mean, in this case, the volume is not 15, right? So it is not bad, not true, but I mean, so in this case, the determinant of this guy is negative 24, and then taking the absolute value, and then we obtain 24. And then the ratio of the area between this rectangle and that parallelogram is 24. So it is originally having the area of 1, and then the area of that parallelogram is 24, right? So that's the meaning of this determinant, okay? And then how can we relate this into this eigenvalue stuff, eigenvalue thing with this determinant, okay? So again, here now we consider this a unit sphere, okay, unit sphere. And then see, in this unit sphere, now instead of I mean using this unit sphere, I mean we just choose two particular axes. So the first one is this guy, and the second one is this guy. But another choice could be the first one is this guy, and maybe the second one is this guy. Okay, and then suppose this vector actually change it into, I mean, after multiplying with the a, and then suppose this vector was changed into like the same vector, but the length is twice, right? And then this guy became still the vector that still has the same direction, and the length is 2, maybe 3, for example. So in this case, this guy became the length of 2, and this guy became the length of 3. So in this case, we can think of this ellipse, right? And in the case of this ellipse, what is the volume, I mean ratio of this volume with compared to the original volume of this unit circle? That will be, that will become like 2 and 3, I mean 2 times 3, which is 6, right? Or if we think of this unit, this rectangle, and then it changes into still this rectangle having the same angle of 90 degrees, and now the lines, I mean this segment, or each of these line segment is having the length of 2 and 3, and thus the volume ratio is 2 times 3, which is 6, right? And then here I assume that we we didn't change, I mean the direction of these two vectors didn't change at all, right? So in that case, if they started from the 90 degree angle, and then they will still have the same 90 degrees, right? But the vector length has changed into 2 and 3, right? So what kind of vectors has this kind of characteristic of maintaining the same direction and having a different but different lengths, or right? I mean different scaling factor. I mean those are corresponding to our eigenvectors, right? Eigenvectors. So I mean even if we didn't prove rigorously about like this kind of arbitrary shape of volumes having the same ratio of this volume in this resulting kind of shape, right? Or resulting kind of volumetric kind of shape. But if we choose some sphere or some unit rectangle that has the line segment as our eigenvectors, okay? And then each eigenvectors will be strengthened, I mean stretched or shrunk with the ratio of its own eigenvalue, right? And then the resulting kind of volumetric shape will have the volume ratio with respect to the input volume as the product of eigenvalues, right? So that's that's how we understand this volume kind of ratio as this determinant, which is also the same as the eigenvalue, the product of eigenvalue, because that product of an eigenvalue is actually the volume ratio when picking up the input shape, whose line segment is our eigenvectors. So does it make sense? 뭐 좀 설명이 좀 됐나요? Any questions? Okay, and then let's just prove briefly why it is true. Okay, why it is true. So this is done by this. So determinant of A minus lambda I being equal to 0. So this is our characteristic equation, right? And all the solutions for this lambda will be our eigenvalue, right? And then we know that we know that the left hand side is the nth order polynomial, right? Which means like some lambda n, and b lambda n minus 1, c lambda n minus 2, and so on, and some constant being equal to 0, right? And then here, yeah, it is typically represented as this. I mean, yeah, if we assume that we obtain the solution, and then it will be lambda minus lambda 1 and lambda minus lambda 2 and so on, being equal to 0, right? So okay, so this part, yeah, is represented as this part as just a nth order polynomial, right? But if we assume that we already obtained the root of the solution, the solution of this equation, and then it will be, yeah, it will have the factored form in this form, right? In this form. So when comparing these two, two equations, they are the same, right? So this is the result of this factored form of the first one, right? And yeah, one thing to note here is that these two are the same for any value of lambda. Any value of lambda. So we actually forget the fact that this is an equation, but we just consider these two different forms. So let me show the example. So for example, we are given this like polynomial representation. This is not an equation, right? And then suppose we obtained this factored form, right? So they are the same, we know that, right? And in this equation, this equation is always true for any value of x, right? So for example, if x is 1, and then it will produce 1 and 2 and 3, and thus it is -4. And then also, if we plug x as 1 and then -2 and -2, which is -4, so these are the same. And if x changes into maybe 0 or maybe 4 and the 5 and -1, yeah, for whatever values, those two left and the right hand side will be always the same. So in other words, it is 이게 항등식이죠, 기본적으로 항등식. So when comparing these two, back to this equation, when comparing these two, we have a freedom to choose any lambda value, and then it will be the same, right? Okay. And then let's choose lambda as 0. Okay. And here lambda 1, lambda 2, and lambda n are particular solution, or these are constant value that are not variable, right? These lambda 1 and lambda 2 are just like these 3 and the -1, right? So these are constant value, right? So we have freedom to choose whatever x value there. So here we choose any lambda value, and particularly I chose lambda as 0, right? And then what is the resulting value? Result when plugging lambda as 0 here. It will be just it will just give us the product of eigenvalues, lambda 1 and lambda 2 and so on, although we have a negative sign over here, right? So the second equation will give us the product of lambdas, right? Or product of our particular eigenvalues of a given matrix, which is like, so when plugging x as 0, and then it will be producing -3, which is the product of our root, right? Okay, so far so good, right? And then yeah, we don't actually use the first one, but we actually use this guy, which is really the original form. Okay, and then if lambda, plug lambda is 0, then what is that? It is determinant of A, right? So we obtained that determinant of an A is actually the product of all lambdas that we, lambda 1 through lambda n, which are our eigenvalues. Okay. Although, yeah, I just ignore the sign, right? Yeah, so this is how we can prove this. And related to this, this characteristic polynomial, we can also obtain this kind of equation, like, yeah, we consider the product of our eigenvalues, and what about the summation of our eigenvalues? So if we think of lambda i's, okay, so can we represent this as a summation of all the eigenvalues? Typically it should be represented as a lambda, because a sigma is typically indicating the singular values, right? So, but anyways, suppose these are eigenvalues, and yeah, so let's just change it. Okay, the summation of our eigenvalues is represented as what? Does anyone know? Yeah, it's a trace of an A, right? So what is the trace? What is the trace? Trace is the summation of diagonal values, right? Diagonal values. So it is 5. And yeah, it is a little bit tricky to. Yeah, it is a little bit tricky to prove, and it is related to this kind of cofactor kind of pattern when computing the determinant. Okay, so although we cannot easily compute the determinant of this given an arbitrary sized matrix of an n by n matrix, but yeah, we can kind of get some patterns. Yeah, so yeah, we obtain this relationship, but yeah, I'm gonna skip this part, okay? But yeah, but one thing that I want to emphasize in this is that so we haven't talked about the similarity transformation, but this similarity transformation is closely related to eigen decomposition. So for example, if we have the matrix A and its eigen decomposition form, which is V and D and V inverse, right? So D is a diagonal matrix, right? Okay, so in this case, we can represent this equation as this form, right? So in the first equation, it is representing the given matrix A as the product of some matrices, and in these product of these 3 matrices, they should be invertible matrix and the one matrix, and in the on the right we need to have its inverse matrix, and in the middle it should be diagonal matrix, right? So this is the requirement to decompose this matrix A into a vector, or the product of the matrix, which is called the eigen decomposition. But if we found this first equation, and then this second equation is just automatically obtained, right? And then this guy is yeah, we can understand this as we are given the matrix A and then multiply some matrix on the right and another matrix on the left, and then the resulting matrix should be diagonal matrix, right? Diagonal matrix. So in this case, it is, yeah, the first one is eigen decomposition, and the second one is called diagonalization, because we diagonalize the matrix A into diagonal matrix, right? So that way we call it as a diagonal matrix. So, so in this case, we can think of some transformation in a general form where, yeah, so here particular matrix V is having the column, the columns of matrix V is our eigenvectors, right? So they are eigenvectors, and if we can find the n linearly independent eigenvectors, and then we can obtain V inverse, right? But what if we just apply any matrix B, which is just an invertible matrix, and then multiply B on the right and B inverse on the left? So in this case, what kind of characteristic does this matrix multiplication have? Okay, so in this case, one important characteristic is that the resulting, suppose we obtain the resulting matrix as C, and then here, does anyone know the important characteristic in this transformation? So in this case, the determinant of A is the same as the determinant of C. So this transformation is called the similarity transformation, right? And why is it called the similarity transformation? It is like, yeah, more intuitively, you can think of it as just a similar transformation. It means we transform a matrix A into another similar matrix to A, right? So that way we call it as a similarity transformation. And in what sense are these matrices are similar? Okay, similar. This being similar. Similarity is defined as like preserving the determinants, okay, of original input matrix and the output matrix. And how we prove it is really easy. So determinant of C is represented as a determinant of B inverse A and B, right? And then we know that this guy, the product, the determinant of the product of matrices is just product of individual matrices. The product of the determinant of an individual matrices. And then also we know that this guy is represented as determinant of 1 over determinant of B, right? So these two guys are cancelled out, and thus the determinant of an A is the same as determinant of C. Okay, so this is called the similarity transformation. Okay, and then here, more interestingly, from the perspective of an eigenvector and eigenvalues, we can also extend this similarity transformation into the following manner. So eigenvalues of A, okay, in this similarity transformation, eigenvalues of an A is the same as eigenvalues of C. Okay, so there is another interesting characteristic of this similarity transformation. So similarity transformation, in other words, preserves the eigenvalue of a input matrix. Okay. So what does it mean by preserving eigenvalues? I mean, eigenvalues are the same, and what does it mean actually? I mean, from the perspective of a polynomial, I mean the characteristic equation. Okay, if the two matrices of A and B, C have the same eigenvalues, exact same set of eigenvalues. So in that case, it means their characteristic polynomial should be the same. Okay, so what it means is as follows. So determinant of A minus lambda I being equal to 0 is actually the same as determinant of C minus lambda I is equal to 0. Okay, so the characteristic polynomial or this characteristic equation should be the same between A and C. So we can also prove this. Okay, so it's a little bit more difficult. I mean, slightly more difficult to prove this guy. Okay, so now we want to prove this guy. And how we prove it is as follows. So C is, again, B inverse and A and B. So here, in this similarity transformation, we can freely choose whatever B as long as this matrix B is inverse, right? So whatever B we choose, they will be cancelled out in this form, right? And thus the determinant will remain the same. And also, these two characteristic polynomial will be the same, and so let's prove it. So C minus lambda I is B inverse and A and B minus lambda I, right? And then here, we apply one simple trick of this identity, represented as B inverse times B. Okay, so we just change the identity as this form, and then in this case we can actually factor it out into B inverse A and B minus B inverse and I and B. I mean, it is still obvious, right? And then determinant of B inverse and A and B and minus. So if we think of this part, and then we have lambda here and B inverse here and identity and B, right? And then now we can apply this guy into here. So in this case, this exact representation is changed into B inverse and lambda times identity times B, right? Okay, so B inverse and lambda I and B, and determinant of B inverse, and it can be factored out into A minus lambda I and P. Okay, so from here to here we just applied like AB minus AC is factored out into A times B minus C, right? And also BA minus CA is B minus C times A, right? We can easily factor it out, right? And so we just apply these two into here. Okay, so now it's time to apply this the determinant property of determinant of B inverse, determinant of A minus lambda I times determinant of B. and so this guy and this guy is cancelled out, and so we obtain determinant over a minus lambda I, right? So what it means is this guy is also some polynomial with respect to lambda, right? So nth order polynomial, and that polynomial is the same as this, and so during this proof or this derivation, we didn't require any particular lambda value, right? So that means it is also, I mean, it is still 그러니까 항등식이라는 뜻이에요. 이게 여전히 항등식. 정확하게 하여튼 어떤 램다든 이제 똑같은 식이다라는 거죠. 그러니까 램다에 대한 그 폴리노미얼 식 자체가 완전히 동일하다. 따라서 이제 식 자체가 동일하니까 이제 그거를 so yeah, because they are exactly the same form, and so if we set it as 0 and set it as set this guy as 0, and then the root or the solution of the first equation and the second equation will still having the exact same solution set, right? Okay, so again, our conclusion is this similarity transformation preserves the exact same set of eigenvalues, and it is because this characteristic polynomial is, I mean, still remains the same. Any questions so far? Okay. And now, oh, okay, yeah. So, back to this diagonalization. So, again, I mentioned that the second form of this guy is called the diagonalization, right? And diagonalization doesn't change the eigenvalues at all because they still maintain the same, exact same characteristic polynomial, right? But when viewing it as this similarity transformation, we have a freedom to choose whatever matrix B as long as it's invertible, right? And suppose we chose B as some other matrix. So for example, if A was like 2653, which is our ongoing running example, and then let me just give some arbitrary matrix B, and we just apply B inverse over here. Okay, in this case, we will obtain some matrix, right? And we know that this guy's characteristic equation or eigenvalue will be the same as that guy, right? That is the that is the requirement, or the that is the characteristic. That is the requirement of this similarity transformation, right? But in general, this matrix will not be diagonal matrix, right? It will be just a full matrix, right? So it will have some values on each of these four elements, right? So this matrix is not diagonal, right? Although it's a similarity transformation that still preserves the eigenvalues, but that is not diagonal matrix. But suppose we found some matrix B. When applying this similarity transformation, we're using B, and then this resulting matrix became the diagonal matrix. Okay, and then this particular matrix is now our eigenvector, and this diagonal matrix, which is the result of this similarity transformation, reveals the eigenvalue. Okay, so again, suppose you carefully choose the matrix B, and then somehow you found such a matrix B that makes this given matrix into the diagonal matrix, and then that diagonal matrix will give you the eigenvalue. Okay, and then it's just a sketch of this eigenvalue algorithm. Eigen decomposition algorithm, which we will study hopefully in the rest of the semester. And suppose you found some matrix B and your matrix became something like this, which is not exactly diagonal, but really close to diagonal, right? So in this case, yeah, we can kind of intuitively think that our eigenvalue is really close to 4 and 2, right? So yeah, so this is a kind of main kind of idea of iterative algorithm to find the eigenvalue and eigenvector. So even though we didn't study that topic yet in more detail, but I mean we already studied one particular way of finding eigenvalues and eigenvector, and how we first compute the we first compute the characteristic equation. We solve for C. Let's see. Okay, so we typically set up this equation, characteristic equation, and solve it, right? And then we obtain the eigenvalues. Then for each eigenvalue, we compute its eigenvector by solving a minus lambda I times x is equal to 0, right? Okay, but what if our matrix is really big, like 100 by 100 or even bigger matrix? And then it will be 100 degree polynomial, right? So it will be really difficult to solve this 100 order kind of polynomial, equation, right? So in that case, we cannot easily compute or solve for that really high order polynomial equations, and so we don't follow that approach. We don't take that approach. In that case, we actually follow some other approach, which I just described, like this. So how we do it is, we just we don't actually find we cannot find our eigenvector matrix of V in this place. All at once. We cannot find it just directly, but somehow you found some kind of imperfect matrix B that actually makes your matrix close to diagonal, like this, right? And then this is our A and this is our C, right? Although this is not an exact eigen value vector, but we found B1 and also B inverse. So 1 is indicating the iteration, the time step in our iteration. And then we found some matrix B, which is closer to diagonal form. And then given this matrix C, and now we find another matrix B2 and B2 inverse. And then this matrix is like 3.87 and 2.13. This is just a hypothetical example, and then it actually made this this matrix even more diagonal, right? So that way we can iteratively apply this similarity transformation over and over, so that we make the resulting matrix more and more, closer and closer to the diagonal matrix, right? So in this case, again, we kept applying similarity transformation, and thus eigenvalues will still remain the same. And then if it is a really close to diagonal matrix, and then now we can conclude that our eigenvalues are 3.87 and 2.12. But how do we find the eigenvectors? what is our eigenvector matrix? Yeah, it is really very easy. So we applied like A times B1 and the B1 inverse, and then we applied B2 and B2 inverse, right? And so B1 and B2 is our final eigenvector matrix, right? So that way altogether, if we call it as B, and then if we call it as V, and then we obtain V A times V, and the V inverse is almost the diagonal matrix. So this is kind of a sketch or overview of iterative algorithm to compute eigenvalue and eigenvector. Any questions so far? Okay. Okay, let's move on then. So for this Fibonacci stuff, I believe you guys can solve it on your own. I hope it was interesting. And one of my students actually created this problem, although he may have found that problem from somewhere else, but he proposed to add this problem in our exam, but not for our own exam, but it was part of our my undergrad level linear algebra exam. Okay, and I think this is also another easy one. And let me just discuss the problem 9. So it is related to let's just go over with the problem statement. If A is symmetric, and then any two eigenvectors from different eigenvalues are orthogonal. Okay, so if you guys remember, then if A is not symmetric, suppose A is just a general square matrix. We at least need the square matrix assumption because we talk about the eigenvector and eigenvalue, right? For the square matrix, and if we choose a different eigenvalues and then their corresponding eigenvectors, okay? So we start from different eigenvalues and then obtain their corresponding eigenvectors, and then these eigenvectors are linearly independent. So eigenvalues are different, and their eigenvectors are linearly independent. Okay, so we didn't prove it, but I strongly encourage you to check out that proof. But in this case, if A is symmetric, they are not just linearly independent. They are actually more strict. They are even orthogonal, right? And then how can we prove that? So suppose A is symmetric, and A times V is lambda 1 V1, and A times V2 is lambda 2 V2. Does anyone know about the proof? Lambda 1 and lambda 2 are different, and then v1 and v2 are orthogonal. I'm trying to remember how we prove it. Okay, let's try. So in this case, yeah. So in order to prove orthogonality, for example, we need this conclusion, right? And then somehow, it seems that we need a V2 transpose, right? And so let's transpose this guy, V2 transpose and A transpose, and lambda 2 and V2 transpose. Yeah, I actually don't exactly remember how to prove it, but yeah, let me try. Yeah, let me give it a try briefly. So starting from the first one, and then let's try to just multiply V2 transpose into the first formula, and then it is V2 transpose and lambda 1 V1, but in this case this is a scalar, and then that can be represented into this form, right? Okay, and then using the second one, we can do we can do the similar thing. So V1 transpose and A V2 and lambda 1 and V1 transpose and V2. We obtained these two by multiplying V1 and V2 on the left hand side of each equation of 1 and 2. Okay, and then so on the right hand side, lambda 2 and V2 times, V2 transpose and V1, and here V1 transpose V2. But these inner products are actually the same, right? A inner product with the B is the same as B is inner product with the A, right? Okay, and then what about the left-hand side? Left-hand side. So let's try to just make them as equal as possible. Okay, so in this case, the first one we multiply V2 on the left and the V1 on the right, and in this case V1 on the left and the V2 on the right. So let's just try to apply the transpose on the for example second equation, and then in this case V2 transpose and A transpose, and V1 is our transpose result, right? So we completely, we reverse the order and then apply the transpose, right? Okay, and then what about the right hand side? The right hand side is still the same. So in this case, it is lambda 2 and this inner product vector, and then this guy will produce just a scalar value, right? And then also, this is also scalar, right? So the scalar transpose is just the same one, right? So it can be just represented as this guy, even if we apply the transpose, I mean, we can just make them, I mean, just remaining the same, right? So far so good, right? Okay, and then if we compare this guy and this guy, okay, so this guy and this guy, now V2 is on the right in both one, on the left, and V1 is on the right. But A and A transpose is different, right? But now it's time to apply the fact that A is symmetric, right? So these two are the same, right? Okay, so we can remove this guy. And let's see, this is a 2, yeah. So if we just subtract these two equations, and then what is the left hand side? Left hand side will be 0, right? Because this part and this part will be the same. So if we subtract between these two, and then it will be just a 0. But what about the right hand side? Right hand side is, this part and this part is our inner product between V1 and V2. But lambda 2 and lambda 1 are assumed to be different number. So it's lambda 2 minus lambda 1 times V1 transpose and V2, right? So we still have the inner product between these two, and this difference between our eigenvalue, and it should be 0. So, okay, so this guy is non-zero because lambda 1 and lambda 2 are different eigenvalues that we are given here, right? Okay, and so this one is non-zero, and this one is the quantity of our interest, and then it should be 0, and so this guy should be 0 because this is non-zero, right? So this is all about the scalar multiplication, right? And so that way we can conclude that V1 and V2 are orthogonal, or their inner product is 0. Okay, so this is how we prove this. And then moving on to the second question. I mean, I'm not gonna apply. I mean, I'm not gonna compute the exact eigen decomposition, but for this given vector, okay, it is just a result of like a multiplication of A over and over with the given vector X, right? So in this case, it is called actually power iteration, right? So we have studied that in this case, the vector direction is converging to the eigenvector that has the largest eigenvalue, right? So if you just obtain the eigenvalue and vector in the first problem, and then you should be able to just obtain the solution. Is this okay? And then the next question might be a little bit tricky. So in this case, in general, this given random vector that we choose, and then if we keep multiplying A over and over, and then this, so it will be converging into eigenvector with the largest eigenvalue, right? But I mean, is there any case that will give us the different results? Did anyone answer the question C or problem C? 네, 어떤 아이겐 벡터랑 일치하면? 네? 네, 그렇죠. 네. Yep. Right. So if you recall or remember this example, right? So we first represent the given input vector as a linear combination of our eigenvectors, right? And in this case, what if, I mean, here, let's assume that V1 is the eigenvector that is the largest eigenvalue, and that is the smaller eigenvalue. And what if our given input vector has a zero coefficient, I mean, as a linear combination when representing it as an eigenvector, okay? In that case, yeah, we have no component for this eigenvector that has the largest eigenvalue, right? So in this case, there is no way to, like, yeah, increase this vector component, right? So the answer is that, I mean, for our problem, the answer is that when the yeah, when our input vector coincide with the other eigenvectors that has the smaller eigenvalues. Okay, in that case, we will not obtain the largest eigenvalue, right? But in general, if we, yeah, I mean, suppose, I mean, we can consider that as really unlucky or really unfortunate case where we cannot obtain the eigenvector that has the largest eigenvalue, right? But in general, if we just start with the random vector, and then we will have some non-zero component over here. So eventually, if we keep multiplying A over and over, and then it will just give us the eigenvector with the largest eigenvalue. So, so this is called the power iteration, and then this is one really simple algorithm to obtain one set of, I mean, largest eigenvalue and corresponding eigenvector. Okay, and yes, if what if we are worried about this unfortunate or unlucky case? Then how can we avoid that? I mean, yeah, one simple way is to just try out several different random vector. Okay, so if the first case, I mean, first chosen random vector was like an unlucky case that has a zero coefficient on the largest eigenvalue. I mean, although it is really very unlikely to happen, but yeah, I mean, in order to, like, yeah, avoid that kind of an issue, we can just try out several different random vector and then apply the power iteration, and then yeah. And then it is also the extension of the first one of this power iteration in the context of a singular value decomposition, right? So in this case, 네. 그러세요. 잘못 냈네요. 잘못 냈네. Okay, yeah, so this problem was wrong, so yeah, let me just quickly fix it in this form. So we are given matrix A and AA transpose, let's call it as B, and let's change it as, oops, yep, okay. So this is B. So what about this case? What will be our answer? So yeah, I'm not sure how much we discussed the details about it. I mean, details about the relation between eigen decomposition and singular value decomposition. But this is our matrix A, which is a U and a sigma and the V transpose, and then A transpose A will be yeah, V and sigma transpose and U transpose, which just transpose this result, right? So this is A transpose, right? And then our A is U and sigma V transpose, and then this guy is becoming identity, and this V, and sigma transpose is just sigma because it's diagonal matrix, and its transpose is the same as the same diagonal matrix, and so it is squared, and V transpose, and thus this is our eigen decomposition form of A transpose A, right? And then we will have the squared value as our eigenvalues, right? And then we have this V, which is these 3 columns as our eigenvectors of A transpose and A, right? So what will be our resulting vector after this power iteration? It will be the first one, right? So this guy is associated with the largest eigenvalue, with this guy. So the resulting vector is like this. Okay, and you can also A transpose, right? And then if we apply C, and if X is a 2-dimensional vector, and then we also obtain now this vector, right? Okay, and also in this form, I mean, let's remind what we proved in this problem, or problem 9. So if A is symmetric, and then we obtain orthogonal eigenvector, right? And so here A transpose A is basically one example or symmetric matrix. So if we transpose it, and then it will give us the same result. And then if we look at this form, we have the diagonal matrix in the middle, and these two parts is V and V transpose. And so V is orthogonal matrix from the definition of the singular value decomposition, and then also when viewing them as eigenvectors of this symmetric matrix, and then now we obtain the orthogonal eigenvectors as for this symmetric matrix. So this is how we how this characteristic that we proved, how this is related to the relationship between eigenvector, eigendecomposition, and the singular value decomposition. Okay, and then what will be the answer for the problem 12? So it's a 4x5 matrix, and it's basically about the permutation stuff, right? So first and the third rows, I mean permuting it in the row-wise manner, and then we have to multiply the matrix on the left, right? So as we discussed earlier in today's lecture, I mean doing something in the row-wise manner, and then it is typically involving the matrix multiplication on the left, right? And then doing some column-wise stuff, and then we multiply it on the left, on the right. So in this case, it should be 4x4 matrix, and then if we change the interchanging, if we interchange between the first and the third row, and then we just change it into this, right? And we have to set them as 0, right? So this is the permutation matrix. And then likewise, we can also obtain the column-wise permutation. Okay, and then the last one. I think this is quite an interesting problem. Did anyone solve this problem? Anyone solve this problem? Anyone? Really? No. Okay. Okay, so A is non-singular. If that is true, and then its inverse has the form of this, right? We have to prove that, and furthermore, we have to find this alpha as well. And it is having the inverse of alpha u v transpose, which has almost the same form except for this scaling factor alpha, right? Okay, so let's try to just multiply them together and then make it equal to identity matrix. So, for example, this times this should be identity matrix, if that is true, right? If this guy is the inverse matrix of the original matrix, and then it should be true, right? And then if we just distribute this multiplication, and then I plus u v transpose plus alpha u v transpose, right? And then the last term will be multiplying this guy and this guy, right? So let's just move the alpha to the left, and then u v transpose u v transpose. Right? And then it should be identity matrix. And so let's just make it, let's cancel it out. Okay, so here, one little trick that we need here is as follows. So it looks like x squared, and we have the same term over here, right? Okay, so in this case, it is really outer product, right? And then, of course, this part can be represented as this form. So far, it is straightforward. But we need to manipulate this term in this manner. So here, let's look at this part. So we have u and v, and u and v transpose, right? So if identity matrix is like a 3x3 matrix, and then u is 3-dimensional, and v transpose is also 3-dimensional row vector, 3-dimensional and 3-dimensional, right? Okay, and then here, about this term in the middle, v transpose and u, and this guy is scalar, right? So that is scalar. So that is important part. And by the fact that it is scalar, we can actually rearrange this guy into alpha, which is also scalar, times v transpose u, which is also scalar, and u and v transpose. So in other words, we compute this part first, which will generate the scalar, and then we just move it to the left. Okay, and then the remaining part is the first u and the last v transpose, right? Okay, so u and v transpose, and it should be equal to 0. Okay, so we have u and v transpose over here, and then if we just factor this further out, and u and v transpose, and what about the scalar term? It's alpha plus 1 plus alpha v transpose u, which is still a scalar, right? And that is, that is 0, right? Okay, so so what is the size of this 0 in this case? Is it a vector or scalar or matrix? What is that? So what is the size of that 0? Is it a scalar, vector, or matrix? It's a matrix, right? So it is matrix. So it should be just a 3 by 3 0 matrix, right? And then, yeah. I mean, so here it is impossible to make this guy as 0 matrix, because in that case, yeah, suppose this guy is non-zero, having at least one non-zero entry. So in this case, okay, so if this is non-zero, I mean 0, and then we can produce 0 column and 0 and 0 column, but if it is 1 and then 0, 0, 1, right? So in this case, yeah, both of them, I mean, so if they are equal to 0, then either of them, yeah, I mean, at least one of them should be 0, right? At least one of them should be 0, right? But if one of them is 0, and then we are just adding 0 as this outer product to this original form of I plus U V transpose, it will be just equal to identity matrix. So it is just a trivial case that we just don't consider, right? So U and V transpose, each of them should be at least non-zero vector, right? To make the non-trivial modification of this matrix I, right? Okay, so this one cannot be a 0 matrix at all, right? Then the remaining part of this scalar part should be 0, right? So if it is 0, and then alpha and plus 1 plus we transpose U, and plus 1 should be 0, and thus alpha should be 1 plus we transpose U and negative 1. So if we set this alpha as this form, and then we make this product as identity matrix, right? So that way this guy will be inverse of the original one. Okay, so that is our solution. Okay, so we found the first part of the problem, I mean the answer for the first part, for some alpha, and then find the expression for alpha. We found that. And then the next part, what U and V makes A singular. Okay. So in that case, yeah, we shouldn't be able to achieve this equation true, right? And then, yeah, how can we not achieve this equation? In this case, yeah, it is simple. So if alpha is not defined, and then that's when we cannot achieve this equation. And when when is this alpha not defined? It is when this V transpose U is negative 1, right? So their inner product. Although we perturbed, or we just added the identity matrix as an outer product between those two, but if we compute their inner product, and then it is producing negative 1 as an inner product value, and then this is making this denominator as 0, which makes the definition of alpha impossible, right? Okay, so is when this U transpose and V is negative 1, and then if it is singular, what is the null of A? So I plus U V transpose, I mean if it is singular, and then what is the definition of the null space? It is the the set of all the possible solution that satisfies this equation, right? That is called the homogeneous equation, where this b part or this constant part on the right hand side is 0. So let's try to solve it. We know that V transpose U is equal to -1, because that's when this matrix is singular. Let's just distribute this multiplication, and then plus okay, so what kind of trick can we apply over here to obtain x? Okay, so let's just try to apply the same trick. So we have U and V as an outer product, and we have x over here, and so V transpose x is our, the scalar value. So x plus V transpose x and U, it can be written in this form. Does anyone have an idea? So here we need to find some non-zero vector v. So that's the solution for this equation. 네.
x는 결국에 그 스페이스는 결국에는 그 U 방향의 라인이 되는 거예요.
그러네요. 그러네요. Yep. Okay, so the student gave the solution, which is insightful. So we have the x over here, and it is this scalar, which is this V transpose x and U, right? And then it should be 0, and we know that U is non-zero vector, right? And then we have a freedom to choose this vector x, but this part is some scalar, right? Some scalar of U, right? And so x also should be in line with vector U, so that we can make the zero vector, right? Okay. I think that's it, because in terms of our null space, yeah, we only need to find the basis. Okay? We need to find the particular direction, right? And once we found that particular direction, and then its scalar multiples can be all the, I mean, it is always the solution also for this, yeah, they are also for the solution for this, they are also the solution for this original equations, right? Yeah, for example, let me show the example over here. Let's see. Yeah, so back to this example. Suppose A is our eigenvalue, and then if we just subtract 8 along the diagonal, and then we obtained this matrix, right? The singular matrix times x equals to 0, and then all the possible solution for x will be the null space of this matrix, right? And then what we did here is that we found the ratio between them, like multiplying 1 and also 1, and then that will, yeah, linearly combine them to make 0 vector, right? And then 1 comma 1 can also be like scalar multiple, like 2 comma 2 and -5 and -5 and so on, right? So really the direction is important, right? So that's why they are called a null space, because null space is subspace that is spanned by some basis vector. Okay. Okay, so we at least found the direction. So that's it, right? Yeah. So this alpha u will be our solution, and also let's check out the, yeah, let's verify this is our solution by just plugging this over here, and then this alpha u plus uv transpose alpha u, right? And then this alpha can be moved out to the left, and v transpose u is what? -1. Okay. So alpha u minus, right? Okay, so we verify that if we set x as a alpha u, and then it will be our null space. Or more exactly, the null space is represented as span of u. Okay, so that completes the solution for the last problem. Yeah, so I think personally the last problem was quite interesting. And any questions? 네. 네. 네, 하여튼 뭐 방향이 저 U랑 같이 똑같은 방향이어야 한다는 걸 저기서 알았고, 그러면 그 말은 이제 그 방향 성분으로 사실 스케일러 멀티플이 모두 다 솔루션이 된다는 것도 우리가 알고 있으니까, 그래서 이제 그렇게 세팅을 그냥 알파 U가 솔루션일 거다라고 한 거고, 뭐 그래서 그걸 대입을 해봤더니 진짜 그렇고요. 네. So yeah, one interesting, I mean, one last thing was, yeah, even though x was involved over here, right? We need to find the vector x, but that vector x itself was involved in this second term, right? But we actually utilize that v transpose x is scalar, right? So altogether, the second term will still have the direction of the vector u, right? So that is the main point. So we don't actually need to care about the x itself in the second term. Okay, so any other questions? Okay, then yeah, let's wrap it up today. So yeah, let's see next week. But yeah, I mean next week I also have some inevitable business trip to somewhere else. So I have to skip the class. I mean cancel the next week's class. So yeah, let's see how can we make up those missing class. So we will not meet next week, but in the following week. Okay, thank you.